Hi Bobcats! In this video we're going to look at the development of the quantum model of the atom. The historical perspective on this is really a great story, and if you're finding this quantum model kind of weird, I strongly recommend you do some more research and independent reading on it because it's really a fascinating story. So we're going to take just a few minutes here to try to describe the development of the quantum model of the atom. This is one of those stories in science that involved literally thousands of scientists working over the span of multiple decades, and in fact even over a century, because there's still work being done on the quantum model today. So the Bohr model was developed around 1913. So after 1913, scientists continued doing more experiments to try to figure out how electrons were arranged in atoms. They found more data and they started asking even more questions about this data. Through about the 1940s, the main parts of the quantum mechanical model of the atom were developed, and again, we're still working on it today. Some of the big names that you'll hear about in the quantum model included Heisenberg, Dirac, Schrodinger, Planck, Pauli, Hund, and there were literally thousands of others working on developing this. To compare the Bohr model with the quantum model, both Bohr and the quantum model talk about the electrons being arranged in shells. Another term that's sometimes used for shell is energy level. The quantum model also subdivides those shells into subshells. So we'll talk about both shells and subshells. Bohr said that the electron orbited in a circular path around the nucleus. We're going to replace that with some three-dimensional shapes. For instance, the simplest orbital is a sphere as opposed to a circle. And we're going to add AL onto the ending of the word orbit to describe this transition from a two-dimensional circle to some three-dimensional shapes. The Bohr model tried to explain exactly where the electron was. In quantum mechanics, we kind of give up on that exact description and go with a probability description. We'll talk about things like there is a 90% probability that an electron is found in a certain region associated with the nucleus or around the nucleus. Both of these models also kind of give up on the explanation of why. A lot of stuff that happens with quantum seems to be counterintuitive. Just like with the Bohr model, they couldn't explain why the electron doesn't just spiral into the nucleus. With the quantum model, it's hard to explain like exactly how tunneling takes place, except that we're describing particles as waves. So when you first start learning about quantum, sometimes it's a little bit uncomfortable because things in the quantum world don't necessarily behave the way we would expect them to. The Schroedinger equation is the main equation for quantum mechanics. You can think of this perhaps as replacing F equals ma from Newton's laws or all of Maxwell's equations. The Schroedinger equation is really what was developed to describe quantum mechanical phenomenon or things that are happening on an atomic level scale. The Schroedinger equation has some really neat properties. One of those properties is that it's something that's known as an eigenvalue equation. Eigenvalue equations are really, really strange. Going all the way back to whenever you first started learning about solving systems of equations, you learned in your math classes that if you have three variables, you need three unknowns. Well, with eigenvalue equations, you can use one less equation than your number of unknowns and still solve the system. So in this particular equation or instance, we have one equation, the Schrodinger equation, and two unknowns. We're going to have E and psi as our unknowns. And we can actually solve this one equation with two unknowns, but there's a trade-off. Instead of getting one unique solution, we're going to get an infinite number of solutions. And towards the end of this chapter, we're going to introduce something called quantum numbers, which are more or less just a system of keeping track of this infinite number of solutions. E is known as the energy of an electron, and psi is something called the wave function. If once we've solved this equation and we have E and psi, we can do a little bit of additional math on psi, because sometimes psi actually turns out to be a complex number or a complex function, which means that it involves I, which is the square root of -1, which is known as an imaginary number. And we want the wave functions to be real, something that we can see in three-dimensional space. And so there's a little bit of math that has to be performed on them to turn these wave functions into a spot where we can find the electron. And so after this math has been done, we end up with this three-dimensional space where there's a high probability of finding the electron, and we're going to call that an orbital. When we go to apply the Schroedinger equation to real atoms, something happens along the way. It turns out that we can only explicitly solve the Schroedinger equation when there is one electron in the species. If we have something like helium that has 2 electrons, we don't have the math to solve the equation. So when it comes to something with a whole bunch of electrons, we certainly can't solve it. These many electron species, and many electron just means anything more than one, well, in order to describe them, we're going to base our description on the hydrogen atom solutions with just one electron, but we need to always keep in the back of our mind that they do not account for electron-electron repulsions, right? So these hydrogen atom solutions do not account for the fact that when you have more than one electron, there are some energy terms associated with each electron repelling all of the other electrons that are present. And so the more electrons an atom has, the more likely it is to deviate from these hydrogen atom solutions. And so you're going to see some weird things happening, like when we go to develop the electron configuration for chromium, we're going to discover it doesn't match the pattern that we develop, and that is simply due to these electron-electron repulsions. Now, if you like math, and I definitely put myself into that category, but I recognize that's certainly not everybody in the world. But if you're one of those people who likes math, there's a link here to a little bit more detail about the math behind the solutions to the Schroedinger equation for the hydrogen atom. I don't want anyone to think I'm going to test you on this. This is math that if you were a math major and you came in as a freshman in college and your first math class was something like calculus or even ordinary differential equations, the math to solve the Schroedinger equation is something that you'd hit probably about your junior year as a math major. So I'm not expecting you to do any of this math, but for people who have an appreciation for math, this would be an interesting website to check out. All right, so with this video, we took a really brief look at some of the development of the quantum mechanical model of the atom. We looked at the Schroedinger equation. We learned that the math to solve it is really, really hairy and quite elegant. And in the next few videos, we're going to take a look at how we use those solutions that have already been developed.